Hello. So last lecture in rigid body dynamics and control was about direction cosine matrix. Now I'm going to further expand on that and talk further about simple application and implementation of direction cosine matrix. So first off, a reminder that direction cosines are used to track the orientation of a rigid body. And to this end, we need to track the angular velocity vector. Recall that we had the angular velocity vector and we formed a skew-symmetric form of angular velocity. So we formed this skew-symmetric matrix, and then this matrix appeared in the differential equation describing the change in direction cosine matrix. All right, so the application I'm talking about now is, so inertial navigation is done using inertial measurement units. You have by now, for this course, you should have already heard about accelerometers and gyroscopes. Accelerometers and gyroscopes are inertial sensors, and they're used to measure angular velocity and translational velocity. So what we do is we attach the sensors to the body, and then we use the information extracted from these sensors to determine the orientation of the body, orientation and location of the body. But we are focused right now on the orientation of the body. So implementation is the inertial sensors are rigidly attached to the body, and we are intended to track its orientation and position. And the outputs, as I explained, measured in body frame. Again, remember the sensor is rigidly attached to the body. Because it's rigidly attached to the body, it simply means that everything that sensor measures, every quantity that sensors measures is in body frame. So so we have that, and then we use that to keep track of the orientation. All right, just a reminder, again, if we have the direction cosine matrix, we can relate any vector in inertial and body frame. And just from our latest lecture, we know that C dot T is Ct omega T. Omega T was, again, our skew-symmetric form of angular velocity. And we have C at time t plus delta t. This is simply the solution of this first order differential equation. C at time t plus delta t is Ct exponential t to t plus delta t omega t dt. Now, so everything here is clear except how we are gonna compute this term. So that's the question we are trying to address today, because omega t comes out of a sensor, and a sensor measures or samples omega t at a certain period. So every, say, 1 millisecond, the sensor measures our omega t and sends our omega t back to our computational algorithm. So now we know that omega t in practice is not a continuous function of time. It is true that mathematically we solved this differential equation. I found the solution of this differential equation. But in practice, this omega t is not a continuous function of time. So now the question becomes, at this point, how we do this integration. So a numerical integration scheme or a signal processing scheme should be used to compute this integral. Again, okay, first off, remember again that omega t, Ct, and Ct plus delta t, these are omega t is in body frame, and Ct and Ct plus delta t represent direction cosine matrix at times t and t plus delta t. So there are various schemes to compute this integral. But one of the simplest one is rectangular, rectangular scheme or rectangular rule. What we say in this rule is, all right, so pay very close attention. So I don't have all the details here. If you have question, email me, but it is basic linear, it is some basic linear algebra involved. Let's do the rectangular rule. So what we don't know, what we are after is this m. I call it m. You can call it anything. T to the t plus delta t omega t dt. Right? So now, in rectangular rule, what we say is that we say, all right, this small delta t, this updating period between one sample and the next sample, the time gap between the two samples is so small that it is a good approximation to assume that omega is fixed during this period of time. Once omega is fixed, then we can simply estimate this integral, because omega is now fixed, comes out of the integral, and it becomes t plus delta t minus t. We only end up having delta t. Agreed? So again, omega t, the delta t is so small, or for our application is such that we can assume that during this update period, omega t is constant. So omega t comes out, and we only end up having omega delta t as the result of this integral. So a simple rectangular rule. You can use other rules, and you have to use other rules if you have a high precision application. If you need to know this, you need to update your direction cosine matrix by far more accurately, then you should use other schemes. So we use that scheme, and we have this m. We have computed m using rectangular rule. Now assume that I call this this term delta. It is again just a name assigned to this term. This simplifies my notation essentially. Essentially, it is for clarity of notation. You don't need to do that. So delta is 2 norm. This is 2 norm, omega 1, omega 2, omega 3, delta t. What is 2 norm? This is a vector, right? For a 2 norm in a vector in your Cartesian system, we square each component and we compute the root square of the result. Now, if you look at this term here, m, what I'm going to do is, if you look at this star, what I'm going to do is, I'm using a Taylor's expansion. So I'm using a Taylor's expansion and expand this exponential function. So if you should already know from your basic algebra course, for example, and you see it in various places, calculus. So if you search the Taylor expansion of exponential function, you have Taylor expansion of exponential function, you have I plus m squared over 2 plus m cubed over 3 factorial. So what happens here is we simply expanded our exponential function using Taylor expansion. The only difference being, instead of e to the x, we have e to the m, and our m is a matrix. It makes no difference. And then I'm going to simplify this. So from here to here, you should be able, using linear algebra, to show that you can simplify this whole bracket, curly brackets, into this form. I plus sine capital delta over delta m plus 1 minus cosine delta, and delta is this term, over delta squared m squared. All right? So from here to here, it's a simplification. Use your basic math skills. If you had any question, you couldn't do it, just email me. You could show that you can always replace higher orders of this matrix, meaning that m cube, m4, with, for example, you can replace m cube with delta squared m. All right? You can simply expand both sides and show that this is true. All right, so I'm going to trust that you can easily do that. You can spend some time and do that. I suggest you definitely do that. And this is the equation we're looking for. Now, if you look at this last equation, this equation can be implemented now. now we can use this equation in practice. So as long as our goal is to use a direction cosine matrix, and also our goal is to use a rectangular rule, we can use this equation to update our direction cosine matrix every time that new samples arrive. So the whole thing, let me summarize what I had. So our goal was to compute direction cosine matrix and also have a practical algorithm which we can implement in our code so that we can update our direction cosine matrix every time new samples arrive. So every time we read omega 3, omega 2, and omega 1, we form this matrix. Every time we form this matrix, we can compute delta. Every time we have computed delta, we have M, so we can, and we have CT. CT is our initial condition. We can then compute our CT plus delta T, or our direction cosine matrix at time t plus delta T. Just pay attention, M is a matrix and CT is also a matrix. Thanks for paying attention and see you next time.